primarily what? Reabsorbed?
Unfiltered?
Secreted?
I'm looking at the question.
Secreted. Whoever said that is correct. Why do you think that's true?
Because you just said that a person took a drug and then it's not getting cleared out, so it has to be unsecreted.
It's
No,
because
not-
drug is being added to the nephron.
Very good, Jesse. That's right. So it's not that it's unsecreted, it is primarily or predominantly secreted. So remember, drug comes in through the glomerulus, right? So drug is the first drug that enters the nephron is through the glomerulus. So glomerular filtration. And then what happens as you move down the glomerulus is the drug is added by active secretion, moving drug from the blood to the nephron. Okay, and then what happens is it gets reabsorbed by passive reabsorption, just passive diffusion from the nephron back into the blood. So if, let's say, 10 liters per hour are coming into the nephron, right? Well, you can't have that much, but let's say 5 liters per hour coming into the nephron, and even more is going out in as far into the bladder and out of the body, and therefore the renal clearance is greater than that. That means drug had to be added to the nephron, right? So the predominant process is secretion. Does everybody get that?
Yes.
Yes. Anybody other questions about that? Because you've got to be able to compare filtration clearance to renal clearance and figure out what the predominant process is. Because then that allows you to determine what drug and disease interaction you might have, right? So once you know the drug is predominantly secreted, you're going to be looking for other drugs that are cleared by the kidneys and renally secreted, and are, if you're talking about an acid, you look for another acid, and if you're talking about a base, you look for another base that have all those qualities, because those are the ones that are going to compete with your original drug secretion sites. Because then you got a love triangle, right? Are you guys understanding me?
Yeah.
There.
I think so. Yeah.
Anybody there? Okay. So now it looks like my computer is more working. My computer was really slow. Were you guys able to hear everything I said?
Yes.
So I'm gonna
It just was a little choppy, but it seems to be coming back now. So
Yeah, I'm wondering. I do have 100 things open here. I wonder if that's okay. Yeah, before there was quite a delay in the picture, which made me think maybe it wasn't working. All right, next. Is this still screen sharing? That's it. Yeah, okay.
Yep.
Number 2, in what types of drugs would you expect an increase in the CSS average as a result of alkalinizing the urine? Okay, so we have an increase in CSS average. So in order for there to be an increase in CSS average, considering we're talking about renal clearance with this particular question, what's going to have to happen to your clearance to cause an increase in CSS average? Everybody says?
Doctor, I'm gonna be
So-
straight up with you. A lot of this stuff I have to retouch on. It's been
All right, that's why we're here.
yeah,
So
sorry.
think with me, if you have an increase in CSS average, what would have had to happen to your clearance in order for there to be an increase in CSS average?
A decrease.
Decrease.
Right, good. Everybody okay with that?
Yes.
I'm wondering, should I move this over? I don't know if drawing helps or not. But yeah, we're going to have a decrease in the renal clearance. Huh? in this case. What process is alkalinizing the urine going to affect? Is it going to affect filtration, secretion, or reabsorption?
Reabsorption?
Very good. Because reabsorption is all about passive diffusion, moving from the urine back into the blood, right?
Mhm.
And it has to be unionized for that to occur. If it's ionized, it's not going to move out of the nephron, is it? So that's why changes in the pH of the urine are going to be a big deal, aren't they, with reabsorption and reabsorption only. Changing the pH of the urine is not going to affect secretion because secretion is that active process where they're just competing for those secretion sites. I think of it as little like shovels that are moving drug from the blood into the urine. Doesn't matter what the pH of the urine is for that, but it does matter when it gets reabsorbed to see if it's going to be in the unionized form so it can get reabsorbed, right? So let's think about that. So we need a decrease in clearance. So what's going to decrease clearance? Is blocking reabsorption or enhancing reabsorption going to decrease clearance?
Enhancing, right?
Right. If you enhance reabsorption, it's moving back into the blood.
Mhm.
And therefore not being cleared. So absolutely right. So if you enhance reabsorption, you're going to have a decrease in your renal clearance. Is everybody okay with that? I think that's a little tricky.
I think that makes sense, at least to me.
Yeah, it does.
Okay. So we're looking for something that enhances reabsorption. So we want then it to be in the unionized form. So if we alkalinize the urine, will an acid or a base be preferring the unionized form?
I think this is where I get confused. Is
Okay.
it a base?
It is a base, you're right.
Okay. Okay.
Do you want me to go through that quickly for you guys or even slow? I don't care.
Sorry, I'm doing terrible with words right now. Okay, let me restart. So I think what I'm trying to ask is, so the base would affect it, like this is going back to like organic chemistry a little bit, right? Because it prefers, yeah, like unionized, and if something is it acidic, then it's going to have more electrons. Is that right?
If it's acidic, it's adding protons, right?
Okay.
It's adding protons. So if it's an acid and you are in a more alkaline environment, right, it's going to be more ionized. The acid is going to be ionized. And that's going to enhance clearance, right? And we want something that's going to enhance clearance, but block reabsorption. And we want something that's going to enhance reabsorption. So we need it more in the unionized form. So if we had an acid, we would need it to be more in a more acidic environment, not a more alkaline environment, like this question is asking.
Okay, I see. So like really reabsorption is going to favor more basic conditions because we're going to have more unionized.
Well, it has, so in this case, the question is asking as a result of alkalinizing the urine. So if we're alkalinizing the urine, the pH is going up. There's less protons added, right? There's a lack of protons. And so that will make bases more ionized.
Okay.
And that's why, wait, did I say that right? Yeah, that's right.
It'll make the bases more
no, I'm sorry. Base is more unionized. See, now I'm mixing it up. I apologize. A base is going to be more in the unionized form in an alkaline environment, right? And that will enhance reabsorption, which will decrease clearance. So it's a base. I said base was right, but I just messed up my explanation. Do you want me to try it all again?
Maybe.
Yeah, just do it. Yeah.
Let me move this over here. Um, okay. So here we have an alkaline, wait, we have alkalinizing the urine, right? So what we're looking for, sorry, I have to move everything out of the way now. Okay, we want does it say increased or decreased? Right, okay, we want increase in CSS average, which means we need a decrease in clearance, right? And a decrease in clearance, because we're talking about changing the pH of the urine, we're talking about drugs that are reabsorbed, right? And if we alkalinize the urine, if we have a base, again, the way I kind of remember this is bases, if you think about Henderson-Hasselbalch, will have the unionized form in the numerator and the ionized form in the denominator. And if we're alkalinizing the urine, we're going to favor what's in the numerator. So the base is going to favor the unionized form. And the unionized form is going to be enhancing reabsorption, therefore decreasing clearance. So the answer is a drug that's primarily reabsorbed that's a base. What will happen if we have a primarily, so it's not all drugs that are predominantly reabsorbed, and secretion really, alkalinizing the urine is going to affect secretion. So we need to decide, is it an acid or a base? This isn't true either. Okay, so if it were an acid, again, if we think about Henderson-Hasselbalch, if we alkalinize the urine, we're going to favor the ionized form. That one is going to, if the acids are going to stay in the urine and increase renal clearance, and if we increase renal clearance, we'll see a decrease in CSS average. So that's the opposite of what we expect to see. So we're not going to have an acid. So the answer is this one here. Does that make sense to everybody?
Yes, can you the acid part though? So if we alkalinize the urine, pH goes up, so it favors the ionized, and then I kind of lost it there.
So if it's more ionized in the tubule, right, Kelly, it's going to stay there, isn't it? It's not, or is this Jamie? I don't know. It's going to get it's not going to get reabsorbed.
Right. Okay, that makes sense. Yeah.
It's going to stay in the nephron, and therefore your clearance is going to increase. If the acid's going to stay and increase clearance because it's staying in the nephron and being peed out, isn't it?
Yep.
Therefore, you're going to see a decrease in CSS average, and you'll see a decrease in half-life, right? If I asked you about half-life.
Awesome. Thank you.
Does that make sense?
Yes, it does. Yeah. Thank you. I'm writing it out too, like kind of how you're literally explaining it so I can.
Well, that's how I do it. I don't know if it's the greatest. And you could think of 17 different questions I could ask you like this, right? When it comes to, let me just, don't I have a whiteboard option here?
Can you click on that draw button at the top?
Draw button at the top.
Word says home, insert, draw.
Yeah, maybe I have to use my mouse. Maybe maybe I have to get rid of the annotation first. Well, okay, well, you know what, I can. it's not a big deal. Okay, let me just get to it. Let me first of all erase all of this. Okay, now I'm going to here. All right. So when you're thinking overall about clearance, okay? Yeah. When you're thinking about clearance overall, the first thing you're gonna have to figure out is it primarily renal or is it primarily hepatic? Right? And how are you going to determine that?
Is that just the FE?
Yes. What does FE mean? Fraction of drug that's showing up in the urine unchanged. So this is really the percentage that's due to renal clearance, right? So if FE is approaching 1, it's going to be primarily renal. If FE is approaching 0 or is 0, is going to be primarily hepatic. Is everybody good with that?
Yes.
Yeah.
All right. So then if you, once you know one or the other, and right now we're working on renal. So the next thing you're going to want to know is, once you know that it's renal, you're going to want to know what's the predominant process. And so you're going to try to figure out, is it primarily secretion or is it primarily reabsorption, right? Why do we want to do that? Because once we know that, we know what drug and disease interactions we're looking for. For reabsorption, we're looking for pH changes of the urine, right? And we're looking for changes in the concentration gradient because we have to have that concentration gradient for the drug. That's what powers the reabsorption, right? Has to have a concentration gradient, has to be small enough, lipophilic enough, and be unionized enough to be reabsorbed, right? So those are the two things we're looking for with reabsorption is pH changes and concentration gradient changes. If we're looking at a drug that's predominantly secreted, then we're looking for an interaction with another drug that's cleared by the kidneys and predominantly secreted. And remember, only acids compete with acids and only bases compete with bases. So if we have a drug that's predominantly secreted that's a base, you're looking for another drug that's predominantly secreted that's a base that would be competing. And then how would you tell who's going to win the ride in the with the tube with that active secretion carrier? Well, then you have to compare the KTSs, right? Do you remember what a KTS is?
Is that have to do with affinity?
Yep, it's the affinity constant, isn't it? So it's just like a Km or a C50 or, it's a Michaelis-Menten affinity constant. So the lower the KTS, the more that drug is going to be favored for the ride into the urine, right? So if you've got drug A and it's got a KTS of 2 milligrams per liter, and then you add drug B and it's got a KTS of 0.2 milligrams per liter, what's going to happen? Drug B is going to be preferred for secretion, isn't it? And therefore, drug A is not going to get secreted because it has a higher KTS. The drug that you were giving isn't going to get secreted, but drug B will be secreted. And your drug A is going to have a longer half-life and a higher CSS average, isn't it? Because clearance is going to decrease. Does that make sense?
It does. I love flowcharts. Like this actually really helps organize a lot of the information because this is where it's been so sticky for me that
Yeah.
like the flowchart thing is this just like helped a lot. As
Good.
minor as it really did.
Good.
So
well, if you look, I don't know if you have time, but if you have time, I put a slide together that says putting it all together. And
okay.
I go through all of this in detail, and it should be a good review for you.
Yeah, that's very helpful.
Now let's talk about the hepatic side. I'm going to erase this piece, okay? It would be good if I actually had like a whiteboard when I'll work with what we have. So if we know that our hepatic clearance, where we have very little of the drug that's arriving in the urine unchanged, which means it's mostly metabolized. Then what do you want to know? You want to know, is it a high E or a low E drug, right? And how do we tell that? Well, that's tricky. I could tell you, I could give you the extraction ratio number, and obviously as our E approaches 1, that's a high E drug. As our E approaches 0, that's a low E drug, right? I may give you hepatic clearance numbers, and then you have to assume a normal Q and calculate that extraction ratio. Does that make sense? Not extraction. Yeah. Yeah. Okay, everybody good? And then once we assume it's either a high or a low E drug, then we know that a high E drug clearance is approximated by Q. And we have to worry about first pass effect, because that fraction that'll escape that first pass through the liver is determined by Q over intrinsic clearance times fraction unbound. But if you remember, most drugs that are high E are also non-restrictively cleared, and the liver sees all of that as 1. And then for our low E drug, clearance is approximated by enzyme activity and binding, isn't it? And the fraction that escapes the first pass effect is approximated by 1. So we really don't have any route effect here, because all of it makes it through the liver. Pretty much all of it makes it through the
Okay, and
Okay.
just as a refresher, you mentioned how like high E is like non-restrictive, and I get that. They see it as 1. What did you say about low E again? It was dependent on, you said binding.
And intrinsic clearance times fraction unbound, remember?
Okay, there it is. Yeah, sorry. I'm
No,
just,
that's okay.
yeah, it's just a good review. So,
And remember, if we want to make changes in dose rate, we want to look at CSS average, but really we want to know what's happening with free, don't we? But we don't have to worry about looking at free, because total will reflect free as long as what? As long as there's been no binding change, right? Because free concentration at steady state is equal to total, I'll say total here so you remember, times fraction unbound. So the only difference is this times fraction unbound. So as long as your fraction unbound doesn't change, the free will be proportional, will go up and down just like total. So you don't have to look at free concentrations unless there's been a binding change, right? A plasma protein binding change. Is everybody good with that?
yes.
Okay. So you like that little review there? Clear
Yes,
on
thank you.
drawings. Okay, so we've answered 1 and 2 so far. Number 3 should be a pretty easy one. A normal creatinine clearance is 125 mils per minute. However, your patient's creatinine clearance is only 33 mils per minute. So what's your patient's renal function? Do you know how to answer that one?
Is it 33 divided by 125?
Exactly right. So this is our gold standard, right? So we just compare our patients. So in order to figure out renal function, and you're given this in your equation sheet. So your patient's renal function, so if we put a star here, your patient's renal function will be your patient's creatinine clearance divided by the gold standard, which is 125 mils per minute. You just need to make sure you're in the same units, right? And in this case, I made it really easy. You just divide 33 into 125. And I think it comes out to be like 0.26. I don't know. Where's my phone? Yeah, 0.26. Okay. And then we use that to, in some cases, to figure out a new dosing regimen and dosing regimen, so dose rate and dose interval for patients that have renal failure, right? That's actually something you will do quite a lot in practice. Especially if you work either in a renal clinic or in a hospital. That's like one of the first things I would do in the morning when I came in the hospital is check out everybody's creatinine clearance and make sure any adjustments are made for their drugs for that day. Okay? All right, your patient has heart failure. So he was recently put on furosemide Lasix, which is a diuretic to help him excrete more fluid. This will block the reabsorption of water in the renal tubule. And remember, if you think about what's happening in the tubule, you've got your glomerulus here, which as you can tell, I'm quite a good artist. I'm being silly, I'm a terrible artist. So the blood will come in through the glomerulus and only free drug will get through the glomerulus. And this is our glomerular filtration clearance, which is GFR times fraction unbound, right? And so drug will enter the nephron here. And so now this is urine, right? And then blood will surround the nephron. So this is blood, and this is blood, and this is urine that's being made, right? So as you move down the nephron, big time water reabsorption, right? Water is being reabsorbed like mad. As you remember, we have our GFR, which is 125 mils per minute. Lord help us if we didn't have big time water reabsorption, because we would be making 125 mils per minute of urine. So we would all be sitting here with leg bags and IVs to stay hydrated, wouldn't we? If we were peeing out 125 mils per minute, this would be an uncomfortable world. So thank goodness we have a lot of water reabsorption in here. And as you reabsorb water, your drug and your other compounds in your urine are getting more and more concentrated, aren't they, as you move down the nephron? And so what we have down here is concentrated urine up, and up here it's concentrated too. So to move drug from the blood into the urine, you have to go against the concentration gradient. So here's where we have secretion, but it has to be active because you're moving against the concentration gradient. That happens in the proximal tubule. And then just before the urine goes out in the bladder, we have passive reabsorption of drug and other things in the urine. And we have to have this being more and more concentrated. If we block this water reabsorption by giving a diuretic like furosemide, what's going to happen? We're going to decrease the concentration gradient and therefore decrease reabsorption, right? Because the concentration gradient isn't what it was. So you're decreasing reabsorption. So what's that going to do to renal clearance? If you're decreasing reabsorption, where is the drug staying? Is it in the nephron or is it moving into the blood?
In the nephron.
It's staying in the nephron, and therefore more of it's being cleared, isn't it? So by giving a diuretic, you're going to increase the clearance of reabsorbed drugs. Does it matter whether they're an acid or a base in this case?
No.
No, because it's just about the actual concentration of the urine. So in which type of drugs would you expect a shorter half-life? So you're increasing the clearance, therefore you're decreasing the half-life. So we're going to be just looking for reabsorbed drugs, right? So only drugs that are predominantly reabsorbed and an acid, well, we don't care if it's an acid or a base. All drugs that are primarily secreted, nope, secretion doesn't have anything to do with this. All drugs that are predominantly reabsorbed, yes. only drugs that are predominantly reabsorbed in a base? No. And this would not affect the half-life? No. So our answer is C here. Does everybody like that? Kind of? Questions?
Like it. More questions
Like
like
it?
that.
Excellent. That one came easy for you, huh, Michaela? I'm glad. All right.
Finally, one of them.
Oh, I'm sure you get all these. Now, your patient is on drug B, which is an acid, which is actively secreted into the urine. So now we're switching, all those other questions were on reabsorption. This one's on secretion. So here's an active process, moving drug from the blood into the urine. So we have an acid, and remember, acids compete with acids for those carriers. He then needs to add drug C, which is also actively secreted in an acid. So they're going to compete with each other, aren't they, into the urine. So drug C has a lower KTS than drug B. I was easy on you. I just said drug C has a lower KTS than drug B. So what does that mean? Drug C is going to be preferred, right? So what's going to happen? If drug C is preferred, what's going to happen to drug B, which is our original drug? Again, if we're thinking about our nephron, and drug B was being secreted into the urine, and now it's not, because drug C is preferred.
So
C
drug
went to the
B,
left triangle. I'm sorry, go ahead.
so would drug B build up because it's not?
Right.
Yeah.
Drug B is going to stay in the blood, isn't it? It's not going to go into the urine like it was. So there'll be a decrease in the renal clearance of drug B, right? And therefore, if there's a decrease in clearance, what's going to happen to CSS average?
Increase.
Yep. We're going to see an increase in CSS average. So what do you want to do with dose rate?
Decrease?
Decrease.
Yep. And how about half-life? If we think about dose interval, half-life is going to be 0.693 volume over clearance. What's happened? Our clearance is decreasing. Therefore, our half-life is going to be longer. Therefore, we're going to extend our dosing interval, aren't we? You like it?
Yes.
And this is the drug interaction I talked to you about, like abusers of drugs will utilize, right? Because if you can decrease your dose rate and give it less often, you get more bang for your buck, don't you? We use it therapeutically as well to try to enhance drugs, or if we need to get higher concentrations of drugs. Good. Are you guys all good with that?
Yes.
All right, you ready to move on to these? This is the speed round. Complete the following statements to make them true. Tubular secretion or reabsorption depends upon the pH of the urine.
Reabsorption.
Right, because this is going to affect the ionization character, right? And therefore affect whether or not it can be passively reabsorbed, right? Diffused, whether it can undergo passive diffusion. Good, so the answer here is reabsorption. Everybody good with that?
Yep.
Yes.
In tubular secretion or reabsorption, ionization character of the drug is important.
Reabsorption.
Again, reabsorption. Very good, Jesse. This is actually, these are related, aren't they? All right. Secretion or reabsorption is dependent upon a Michaelis-Menten process.
Secretion.
Secretion. And that's because, remember, Michaelis-Menten is an active process, and secretion is our active process that occurs in the kidney that requires energy, requires a carrier system. Therefore, you have a capacity and affinity just like Michaelis-Menten, right? We have our Tmax, which is our number of carriers, and then our KTS, which is our relative affinity of which drug is going to be preferred. It's the concentration where half of the carrier systems are being utilized. Okay, y'all get a good sense for that? All right, tubular secretion or reabsorption can only be achieved by an active process. Well, I just told you that. Everybody says
Secretion.
secretion. Very good. Tubular secretion or reabsorption is dependent upon a concentration gradient. Which one needs a concentration gradient to power it?
Reabsorption.
Very good. Does tubular secretion or reabsorption site, which of these sites can be overwhelmed or saturated?
Secretion?
Very good. Yeah. We have a fixed number of secretion sites. Remember, reabsorption is just passive diffusion. So there's no carrier system or anything that we can overwhelm. Now, just to be clear, there is such a thing as active reabsorption. There are some things like glucose is actively reabsorbed. There are some drugs that are actively reabsorbed, very few though. Actually, another one is lithium. Lithium is used to treat some bipolar disorders and other psych diagnoses. And lithium, if you remember lithium, it's an ion or it's an element, right? So it's in your periodic chart. And those of you that have memorized your periodic chart, which I know you all have, just kidding, of course, that lithium is in the same family, in the same column with sodium. And we actively reabsorb sodium, and sodium and lithium are treated the same by the kidney. So there's active reabsorption in some cases. I don't mean to confuse you, but I don't want to oversimplify and think that there is no such thing as active reabsorption, because there is. But most drugs are passively reabsorbed and actively secreted. Okay, which one is a passive process?
Reabsorption.
Very good. So these were too easy for you, right? But I hope that kind of cements like the differences between these different processes. They're very different, aren't they?
Dr. Earl, is this document somewhere in Canvas?
I'll put it in there for you.
Okay, thank you.
Sure. And you'll have this recording too if you want it. Okay. All right. So do we have both hours today? Do you know?
I believe yes.
Okay. So I'll just go until you guys are tired of me. I have to leave. What time do I have to leave? I probably need to leave a little bit before 4, but right around 4 for signing day. So, all right. Questions 7 through 10 refer to the following data about X and Y. So now we're changing from renal to hepatic, aren't we? Okay, so we've got 2 drugs that are hepatically cleared. We can see they're both highly protein bound, aren't they? One's bound to albumin, one's bound to AAG. One has a much larger clearance than the other. So let's talk about how we can use this to determine. Remember, once we get into hepatic clearance, we want to determine, is it a high or a low E drug, right? So we need to determine the E, don't we? I told you could take considering that your total body clearance is going to be hepatic because it's all cleared by the liver, your hepatic clearance is going to be equal to Q times E. And if we assume a normal Q, and again, this is given to you in your equation sheet, is 90 liters per hour, we can determine the E for both of these drugs, right? So for drug X, clearance is 72 liters per hour. It's equal to 90 liters per hour times E, right? So 72 divided by 90, this is going to be a high E drug, isn't it? So it has an E of 0.8. So this is a high E drug, and we could tell that before we did the math, right? So this is a high E drug, and our other drug, drug Y, is 12.7 liters per hour, and it's again a Q of 90 liters per hour, and we can solve for E. So 12, having trouble with my calculator, with my fingers, divided by 90. So this has an E of 0.14 or 14% versus 80%. So high E, low E, right? And we probably could have determined this, by looking at our bioavailability too, right? Or at least we could have determined one of them by looking at our bioavailability. If our bioavailability is 0.85, what does that tell you? Well, that tells you can't have a low FH, right? Because F is equal to FA times FG times FH. And if the product of all three of those is 0.85, all of the lowest any of them can be is 0.85, right? So we know this is going to be a low E drug right away when we see this bioavailability of 85%. When we see this low bioavailability of 0.09, we think, oh, maybe that's a high extraction drug because a lot of it is being eliminated before it's getting to the systemic circulation. But we can't be sure that that's a high E drug unless we look at the clearance, because clearly a drug could have a low FA or a low FG and still have a high FH, right? Does that make sense to everybody? Well, they both have high FAs, but we don't know the FG. So this could have a low FG. So maybe it's very highly cleared by enzymes in the gut wall or by P-glycoprotein, right? Are you good with what I'm saying?
Like, so you're saying the low FG possibly makes the F low, like the overall bioavailability.
Right. So we can tell for sure that this is a low E drug, but we don't know for sure this is a high E drug just by looking at the bioavailability, because we don't know what FG is, right? So if FG, let's say if FG were 0.09, FH and FA were both 1, this would be a low extraction drug, but it just has a lot of the drug removed in the gut wall. Does that make sense?
Yeah, that makes sense. Thank you.
We can't necessarily tell when there's a low bioavailability what drug it is, but if it's a high bioavailability, we know for sure it's not highly removed by the liver, right?
Right.
Does that make sense to everybody? All right, so what do they want to know? Drug X exhibits what? Restrictive or non-restrictive clearance? Okay, what does restrictive and non-restrictive clearance mean? Restrictive clearance is when only free drug is available to be cleared, right? So restrictive means that your extraction ratio is limited to just fraction unbound drug, right? So E cannot be greater than the fraction unbound. Only free drug is available. Non-restrictive is when the E is greater than the fraction unbound, right? So let's see what are each of these drugs. So if we compare our E, which I erased already, but this one was 0.8 and this one was 0.14, right? So, and I forget I think we asked about drug X. So drug X has an E of 0.8 and has a fraction unbound of 0.15. So is this drug X, is it only clearing free drug? Well, only 15% of the drug is free, but it's clearing 80%, right? So the E is definitely greater than the fraction unbound. So this is non-restricted, which is what we usually see with high extraction drugs, which we knew this was a high extraction, right? Drug Y, on the other hand, drug Y has an E of 0.14 and 20% of it is available. So it's, again, it's extracting less than what's available. So this is, the E is less than or equal to 0.2. You follow that? So to answer this question, to answer this question, drug X exhibits non-restrictive clearance because E in this case was 0.8 and fraction unbound is 0.15. So therefore E is much greater than, so E is greater than fraction unbound. Non-restrictive. Drug Y, on the other hand, is restrictive because here the E is 0.14 and the fraction unbound is 0.2. Therefore, E is less than or equal to, and in this case, less than the fraction unbound. Is this good with everybody? Questions, comments? Are you still there?
Yeah, I think I'm okay on it. I think.
Okay. Anybody else? Jesse?
I'm still here.
What are you thinking? Is this making any sense?
I think so. I'm definitely going to come back and watch this again.
Okay. So when we think about this, like for this first one, drug X, there's only 15% free. But it's clearing 80% as it goes through the liver. So clearly it's taking more than just free drug, isn't it?
Yes.
And if we compare that to drug Y, where 20% is free, but we're only eliminating 14%, so we're limited but to only free drug here.
Okay, got it. That makes sense.
All right. I know it's a little convoluted, so you just have to slow down and think it, I'm thinking like of drug that's unencumbered by a protein coming at me, can I clear it or not? Is it available? And if we're taking 80% out and only 15 is unbound, we know we're taking more than just bound drug. Okay. If drug Y, which as I remember, it is a low extraction drug, is given PO and drug Z is added. Okay, I don't know about you. I have to draw a lot. Okay, so drug Y, which is low E, is given PO. Drug Z is added that's also highly bound to AAG and has a KD of 0.2 for AAG. So drug Z has a KD. Drug Z has a KD of 0.2 milligrams per liter for AAG, and drug Y has a KD of 8.6. So drug Z is going to be preferred to be bound to the AAG. So what's going to happen to our drug Y? Drug Y is going to have an increase in the fraction unbound because drug Z is going to be preferred because it has the lower KD, right? So drug Y, so I would have to write this down. Drug Y, what's happening is it has an increase in fraction unbound. Drug Y is a low E drug. So what's going to happen to the bioavailability of drug Y? Well, bioavailability is equal to FA times FG times FH. A low E drug, FH is approximated by 1 here, right? So does a change in binding affect FA or FG? No. What determines FA? Well, it has to be small enough. It's got to passively diffuse. through that gut wall, right? And things that affect that are things like complexation and other things that will affect FA and protein binding in the plasma. We're not in the plasma even yet, isn't going to affect FA. FG, again, we're not even in the plasma yet. What can affect FG? Well, P-glycoprotein and the CYP system in the gut wall. Does that have anything to do with plasma protein binding? No. So this is going to be no change here, right? No change. How about the volume of drug Y? What's volume determined by? VSS, VP plus VT, fraction unbound in plasma over fraction unbound in tissue, right? And what has happened? We've got an increase in our fraction unbound in plasma for drug Y, and therefore we're going to see an increase in our volume, aren't we? How about clearance of drug Y? Clearance, in this case, since it's a low E drug cleared by the liver, is going to be dependent upon enzyme activity and binding, isn't it? And what's happened here? We've had an increase in our fraction unbound, therefore our clearance will increase. Are you good?
Yeah, I think that makes sense.
Anybody else?
It makes sense to me.
Good. I'm going to keep moving. Oh, so we have more with drug Y when there's been a, again, we've got an increase in fraction unbound and it's a low E drug, right? So a low E drug clearance is approximated by intrinsic clearance times binding, and FH is approximated by 1. What's going to happen to the CSS average of drug Y? Well, CSS average. The next one we're going to be asked about free. So CSS average is equal to bioavailability times dose rate all over clearance, which in this case, we have to think about the fact that it's a low E drug. So low E is going to be FA times FG times FH, which is approximated by 1 times dose rate all over clearance, which for this drug, because it's a low E drug, is intrinsic clearance times fraction unbound. And again, what's happened? It's been displaced from its plasma protein binding site. So clearance increases and our CSS is going to decrease, isn't it? And how about free concentration? Well, total and free will act the same way unless there's been a binding change. And in this case, there has been a binding change. So I'm going to I'm just going to multiply this whole thing times fraction unbound to determine free. These will cancel, right? These both will go up and will cancel. If you think about it, so the drug is displaced from its plasma protein binding site. So the fraction unbound goes up. So you think about, oh, my free concentration is going to go up. Yeah, until it gets to the liver. And once it gets to the liver, the amount that's available to be cleared, or the fraction that's available to be cleared, will also increase to the same extent. And therefore, it will negate that increase for our free concentration. So no change in free concentration at steady state. And how about half-life? Half-life is equal to 0.693 volume, which is determined by really this ratio between plasma fraction unbound in plasma and fraction unbound in tissue all over clearance, which for this low E drug is going to be intrinsic clearance times fraction unbound in plasma. So again, these two things will cancel each other out because they're both going to be increasing, right? We said above that both volume and clearance will be increasing, but they'll be increasing to the same extent. So they're going to negate each other, right? So there'll be no change in half-life. So we're not going to need to make any changes in the dosing regimen in this case, are we? even though a lot is happening. And you may have to talk your team out of possibly increasing the dose rate, because they're going to see a decrease in the total concentration at steady state. Tricky. Are you good? So quiet. It's a lot, I know. But hopefully this recording is working and you can go back and review if you want to.
Yeah, I'm
All right.
just taking it all in.
Yep, it's a lot. It's a lot.
It's raining here today too, so I'm just
It's
kind of
raining. I have no idea what it's doing. I've been in my office, which has, well, maybe you've not been in my office, but there's no windows in here. And when it's really raining hard, I can tell, because it's really bad, noisy in here, but can't hear. It's not raining hard, at least. It's just kind of a dreary day, but it's, Friday. You get to see all these excited freshmen come in before we crush them, right? I'm just kidding.
Oh
But
gosh.
I do feel like they come in so excited, and then they hit their first chemistry exam and they're like,
you just watch the light leave their eyes a little bit.
Exactly. I feel so bad. So I have to go over and enjoy how happy they are right now. Oh, shoot. Anyway, okay. And they're so happy too, because I just got to see the students that are graduating in a month, and they're all so happy too. So that's nice. Get to see them in the beginning, and of course they changed so much. It's 6 years, so you see so much change. It's really wonderful. Anyway, all right, drug X is given. So we're back to drug X. Drug X is high E, right? Non-restrictively cleared. So we're thinking clearance is determined by Q, and the fraction that escapes the first pass effect is Q over intrinsic clearance with this weird fraction unbound that's seen by the liver as 1. But we do have this first pass effect that makes, that gives us route dependence. So here we're giving an IV, and you say, thank you so much. Drug is being given IV, so we don't really have to worry about this first pass effect. Your patient is on drug W, which is now being discontinued. So, we often, I think I've said this many times, but we often are really on high alert when drugs are added, because we think of drug interactions, but when they're discontinued, there's also drug interactions, right? So the patient was on drug W, which is now being discontinued. Drug W is also highly bound to albumin and has a KD of 0.15. So drug W is 0.15, drug X is 25. So obviously drug W has a higher attraction for the albumin. So what's going to happen when we discontinue drug W? What's going to happen to our drug X? It's now going to be more highly bound, isn't it? Because this high affinity drug is being discontinued, and now drug X is going to have more opportunity to be bound. So you're actually going to see a decrease in fraction unbound of drug X. Does everybody follow that?
Yeah, like a side question that doesn't really have to pertain to class, but like in practice. So like in the hospital, if a drug's being discontinued, how do you look up these KD values? Is there like a resource for that?
Well, you can look up the KD values. You'll get to know the ones that are important as you're in practice, and new drugs are coming out all the time. So you just kind of, you can, like Lexicon or Micromedics may have it, but they may not too.
Right.
And really, you only need to worry if they're highly bound to begin with, right? So you can look all that up pretty easily.
Okay.
Maybe even ChatGPT knows it. I don't know. I haven't checked yet. All right, volume of drug X. So what's gonna happen to the volume of drug X? So volume is really, we're focused on this part, right, about the binding changes. And we know there's going to be, our drug X is going to have higher binding, which means a smaller fraction unbound, and therefore a decrease in volume of distribution, right? And what about clearance? Clearance is pretty straightforward. Clearance is really just dependent upon Q because it's a high extraction drug. Therefore, will binding changes affect it? Nope, no change. Okay, and how about CSS? This is total drug, right? Is we don't have to worry about bioavailability. I was going to write bioavailable dose rate, but since it's given IV, we don't have to worry about bioavailability. So it's going to be dose rate divided by clearance, which in this case is Q. And again, is a binding change going to affect that? No change. Okay, and then how about CSS free? Okay, so CSS free is going to, and again, we can look at total to reflect what's happening with free as long as there's no binding change, but there's been a binding change in this case, right? So we're going to have dose rate over clearance, which in this case is determined by hepatic blood flow, times fraction unbound. And what's happened? We've had a decrease in our fraction unbound. Therefore, we're going to have a decrease in our free concentration. So what are we going to want to do here? This probably means we're going to need to increase our dose rate, doesn't it? Even though there's no change in total. So this is a case where you could see some side effects and you're thinking, why are we having toxic side effects in this patient and there's been no change in their total concentration? Well, this is an example of where you could see that. And how about finally half-life? Half-life is equal to 0.693 volume, and our volume is dependent upon our binding. And what's happened here, we've had a decrease in our fraction unbound. So we're going to have a decrease in our volume, which we already decided. And then clearance is determined by Q, and binding isn't part of that. So again, we'll see a decrease in our half-life. So we're going to need to decrease our dose rate because this is going up, right? Decrease our dose rate and decrease our tau in this case, if we were asked. Are you good?
Yeah, I think this makes sense. I just need to
That's
go
all I
through a few
had.
more.
Hopefully that goes over all the real important stuff that, you know, I expect you to know. It's not going over every question I'm going to ask, of course, but you have the quizzes and that I went through. You have this now, you have the putting it all together slideshow that you might want to look at, and also, of course, the practice problems. I'll add this homework sheet that we just went over to your where did I put all your prep, wherever I put all your prep materials. Did I make a separate module for you? I don't remember now.
I think it's
Did I
just
put it-
underneath the module.
It's under what?
I think it's just underneath like that week's module. So
In
I
the
don't know.
renal. I think it's
Yeah.
maybe in the renal. Okay.
Yeah.
Okay.
Off-topic question.
Yes.
Will you be our advisor through our
Next year.
entire time? Well, yeah, next year and going until we
Well, I
graduate.
think the plan is that I'm not, but
Oh, that's sad.
because I think I'm going to be the advisor for the newbies.
They don't need you. We need you.
Yeah.
We need you.
Who's gonna
Yeah.
be yours then?
Good luck, people.
We're our own advisor now.
I know, right?
Yes, you know. We could talk about that. I think we're planning for you guys to go there, folks. But you know, I always have students because I had to get rid of all my, I shouldn't say get rid of, I had to move all my other advisees that I had before, which was like 40 of them, to other people. And some of them came in, I have to have you. So I'm a softie, you know, so I'll keep some, I'm sure. But most of you, you're going to find other people you want to be with. You just don't know that many people yet, you know? So
what if they just do like a you keep us and then, moving forward you take them,
You
like
guys make me feel so loved and wanted,
you
but
are.
there's great people here that you will love. We'll discuss. We still haven't figured any of that out, to be honest with you. It's on my docket for a next week meeting if you want to know the truth. So we'll work it all out.
Now,
And
can
you can
all
always
teachers
come
be?
to me. You can always come to me if you need something,
Well,
no
that's
matter
good.
what, no matter who your advisor is. I still have people that have other advisors, but then they come to me too, so it's what I'm here for, is to help you. So
Are all professors like advisors or just like certain?
no,
Okay.
no. And what I'm trying to find out from you guys, like what you really want to do and try to maybe match you up. And I think I'm gonna probably ask you guys to fill out a little kind of profile so that we know exactly what you're interested in, what you're not interested in, and how much you want to explore. Do you want to do research? Do you not want to, so that we can try to match you up with a good advisor that will be able to help you and get you where you want to be. Because a lot of, when I talk to some of you guys, I'm like, oh, you know what? I'm not going to help you at all in this. So here's who you need to talk to. You know what I mean? I can't help you in that. So let me have you talk to this person. Right? So
Gotcha. That makes sense.
Well, thank you, Dr. Earl. Please don't forget to upload that document. I really want to
I
try
will
to
do it
fill that
right
out.
now. If I don't, you email me and remind me, okay? But I'll do it
Okay.
right now before I go over to the
Are you
signing.
gonna put it in the renal module or?
I'm gonna put it wherever I put the rest of the stuff, and then I'll announce that it's there, okay?
Okay, thank you.
Are you guys able to retrieve the Zoom calls or the Zoom recordings, okay?
Yeah.
Yeah.
And is there a key for this document that you did
I
today?
was gonna look for one. That's a good question, Jesse. I was gonna look to see if I have a key somewhere for it. If I do, I'll put,
Okay.
okay?
Okay, great. Thank you. I might use it and make it into a Quizlet or something. It looks like a good.
Yeah, because these are
Good.
good questions I can ask, right?
Yeah, absolutely.
You
And then
guys
just
can,
make sure
you
they
guys
have an
can figure
understanding.
out what I'm gonna ask you, I mean, it's,
Was that a hint, 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 hint?
well, I mean, like, as I said, when you make, when that, that table that I
Yeah,
did, you
that
can just
table. Yeah.
point to a thing and you got a question, point to a box. Right?
Yeah. Yeah. Gotcha.
Okay, well, happy Friday. Enjoy the freshmen.
Thank you. I hope you have a good weekend. And I know you have a quiz in kinetics. So yay. And then I'll be having that. I'll send you also the Zoom link for the 12 o'clock noon review that I'll have. And I just answer questions that everybody, whoever's there, brings. So I don't prepare anything. I just come and answer questions. So.
Okay,
Okay.
sounds good.
Sounds good. Thank you so much, Dr. Earl.
Thank you.
Have a good
Thank
weekend.
you, Earl.
Bye.
Bye-bye.
Bye.